At 150 million degrees Celsius, any physical container would instantly vaporize, so we built a bottle made of nothing but invisible force fields. This is not a concept from science fiction, nor is it a miracle. It is the most complex engineering challenge ever undertaken by humanity. To replicate the power of the stars here on Earth, we have had to master the art of containing the uncontainable. We are building a magnetic cage, a masterpiece of physics and mechanical precision designed to hold a sun in a vacuum. This is the story of the Tokamak, the superconductors that power it, and the relentless engineering required to secure the future of clean energy. To understand the cage, we must first understand the beast inside. Nuclear fusion is the process that powers every star in the night sky. In the core of our sun, gravity is so immense that it crushes hydrogen atoms together until they fuse into helium, releasing a gargantuan amount of energy in the process. But on Earth, we don't have the luxury of stellar mass to create that kind of pressure. To compensate for the lack of gravity, we have to turn up the heat. While the sun's core sits at about 15 million degrees, our terrestrial reactors must reach temperatures exceeding 150 million degrees Celsius. At this point, matter ceases to be a solid, liquid, or gas. It becomes plasma. Plasma is often called the fourth state of matter. In this state, electrons are stripped from their nuclei, creating a roiling, chaotic soup of charged particles. Because these particles carry an electric charge, they are susceptible to magnetic forces. This is the fundamental loophole that allows us to build a reactor. If we cannot touch the plasma with physical walls, we will hold it with magnetic fields. However, building a container out of magnetism is like trying to hold a balloon using only rubber bands without letting the rubber touch the surface. If the plasma touches the walls of the reactor, two things happen, and both are catastrophic for the process. First, the plasma instantly cools down, killing the fusion reaction. Second, the wall of the reactor is damaged or vaporized by the extreme heat flux. The most successful design for this magnetic container is the Tokamak. The word is a Russian acronym for toroidal chamber with magnetic coils. Its shape is a torus, or more simply, a donut. But why a donut? Why not a sphere or a cylinder? If you use a simple cylinder with magnetic coils wrapped around it, the plasma will simply leak out of the ends. If you try to bend that cylinder into a circle to close the loop, you create a new problem. The magnetic field lines on the inside of the curve become more compressed than the lines on the outside. This gradient in magnetic strength causes the charged particles to drift apart, ions moving one way and electrons the other, quickly destroying the confinement. To solve this, engineers had to get creative. They realized that by twisting the magnetic field into a helix, like the stripes on a candy cane, they could cancel out this drift. In a tokamak, this is achieved by combining two different magnetic fields. The first is the toroidal field, which runs around the long way of the donut. This is created by massive D-shaped coils surrounding the vacuum vessel. The second is the poloidal field, which runs the short way around the plasma. This field is actually generated by a massive electric current flowing through the plasma itself. When you combine these two, the magnetic field lines wrap around the torus in a spiral. The particles follow these spiral paths, constantly moving from the inside to the outside and back again, effectively averaging out the forces and staying confined.
But generating these fields requires an astronomical amount of electricity. If we used traditional copper wires, the resistance would generate so much heat that the magnets themselves would melt long before the plasma reached fusion temperatures. This is where the engineering of superconductors becomes the backbone of the project. Superconductors are materials that, when cooled to near absolute zero, conduct electricity with zero resistance. This allows us to run massive currents through them indefinitely without losing energy to heat. At the heart of projects like ITER, the International Thermonuclear Experimental Reactor, we see the pinnacle of superconducting engineering. These magnets use fibers of niobium tin and niobium titanium. To keep them in a superconducting state, they are bathed in supercritical liquid helium at 4 Kelvin, which is minus 269 degrees Celsius. Think about the engineering contrast here. Inside the vacuum vessel, we have plasma at 150 million degrees, the hottest place in the solar system. Just a few meters away, separated by vacuum and specialized shielding, we have superconducting magnets at nearly absolute zero, some of the coldest points in the universe. Managing that thermal gradient is one of the greatest mechanical feats in history. The scale of these magnets is difficult to comprehend. In the ITER design, the central solenoid, the backbone of the magnetic cage, will be strong enough to lift an entire aircraft carrier. It consists of 6 modules stacked together, and it acts as the primary transformer to drive the current through the plasma. When we pulse this magnet, it induces a current of 15 million amperes into the plasma. This isn't just about containment, it's about control. The magnetic cage isn't a static structure, it is a living, breathing system that must react in microseconds to the instabilities of the plasma. Plasma is notoriously unstable. It behaves like a turbulent fluid, prone to kinks and wobbles that can cause it to lash out and hit the reactor walls. These are known as magnetohydrodynamic, or MHD, instabilities. To counter this, engineers install sets of correction coils and use sophisticated diagnostic sensors that monitor the plasma's position thousands of times per second. If the plasma moves even a fraction of a millimeter off course, the magnetic fields are adjusted instantly to push it back into the center of the cage. It is a high-stakes game of magnetic puppetry. Another critical piece of the engineering puzzle is the divertor. Even in a perfect magnetic cage, some waste is produced. In a fusion reaction, helium ash is created, and it needs to be removed so it doesn't smother the fire. The magnetic field lines at the edge of the plasma are intentionally diverted toward a specific area at the bottom of the reactor. This is the divertor, the exhaust pipe of the Tokamak. This component faces the highest heat flux of any man-made object. To survive, it is armored with tungsten, the metal with the highest melting point, and backed by high-pressure water cooling loops. The engineering required to join tungsten to copper cooling pipes, given their different rates of thermal expansion, is a masterclass in material science. We also have to consider the neutrons. The fusion of deuterium and tritium releases high-energy neutrons. Unlike the ions and electrons in the plasma, neutrons have no electric charge. This means the magnetic cage cannot hold them. They fly straight through the magnetic field and slam into the walls of the reactor. This is actually intentional. The kinetic energy of these neutrons is what we will eventually use to heat water, create steam, and turn turbines to generate electricity. However, this constant bombardment of neutrons causes the structural materials of the reactor to become brittle and radioactive over time. Solving this material degradation is the current frontier of Tokamak engineering. We are developing breeding blankets, modules that line the inside of the vacuum vessel. These blankets serve 2 purposes. First, they absorb the neutron energy to produce heat. Second, they contain lithium. When a neutron hits a lithium atom, it creates tritium, one of the 2 fuels needed for the reaction. This creates a closed-loop fuel cycle, where the reactor literally breathes its own fuel as it operates. This is a level of resource efficiency that no other power source can match. As we move toward the mid-2020s and into the 2030s, the focus is shifting from "can we do it?" to "how can we make it practical?" While ITER is an experimental machine designed to prove that we can get 10 times more energy out than we put in, the next generation of reactors, like DEMO, will be designed to actually put power onto the grid. Simultaneously, private companies are exploring high-temperature superconductors, or HTS. These materials can operate at slightly higher temperatures, and more importantly, can generate much stronger magnetic fields. Stronger magnets mean we can build smaller, cheaper, and more efficient tokamaks. The engineering of the magnetic cage is a testament to what we can achieve when we stop looking for magic and start looking at the math. We are taking the most violent, energetic process in the cosmos and taming it within a web of magnetism. There is no fire here, only the movement of charged particles guided by the Lorentz force. There is no smoke, only the silent hum of superconducting magnets and the flow of liquid helium. The transition to clean energy is often discussed in terms of policy and economics, but at its core, it is a hardware problem. It is a problem of heat transfer, material limits, and electromagnetic control. Every time we successfully pulse a tokamak, we are proving that we have the technical maturity to handle the energy of the stars. The magnetic cage is more than just a piece of engineering. It is the bottle that will hold the future of our civilization. We have spent decades refining the geometry of the torus, perfecting the cryogenic cooling of the coils, and developing the algorithms that stabilize the plasma. We are now at the threshold where the energy required to maintain the cage is less than the energy produced by the star within it. This is the break-even point, the holy grail of plasma physics. Once we cross that line, the world changes forever. Fusion power offers a source of energy that is virtually inexhaustible, produces no long-lived radioactive waste, and has zero carbon emissions. It is the ultimate goal of clean energy research. And it is all made possible because we learned how to build a bottle out of nothing but force. The engineering of the magnetic cage is not just about making a machine, it is about proving that humanity can master the fundamental forces of the universe to ensure its own survival. As we look at the massive steel structures of ITER, or the compact high-field designs of the next generation, we see the culmination of a century of scientific progress. From the first theoretical papers on fusion, to the first Soviet tokamaks, to the global collaboration we see today, the journey has been long, but the goal is now within sight. We have built the cage. We have learned the language of the plasma. Now we are ready to turn on the sun. This isn't magic. This is pure, relentless engineering. It is the result of thousands of designers, physicists, and technicians working to solve the most difficult how-it-works question in history. The magnetic cage is holding, the star is forming, and the future is finally beginning to glow. Thank you for joining us on this deep dive into the engineering of the magnetic cage. The path to fusion is paved with complex challenges, but each one we solve brings us closer to a world of limitless clean energy. If you are fascinated by the mechanical and digital systems that power our world, stay tuned to Not Magic. We will continue to deconstruct the most impressive engineering feats of our time, proving that behind every seemingly impossible achievement lies a foundation of solid science and brilliant engineering. Until next time, remember, it's not magic, it's the way the world is built.